You can see I have it selected to the volts mode, and this is currently with our half cycle line simulator running. So we'll just give it a single pulse off of this generator and let's see what happens. Let's try it in the milliamp mode. Fuse should still be okay, maybe. Don't attempt to replicate anything that I'm about to show you at home. Again, I can't stress this enough, but don't ever attempt to modify your handheld meters. There's a very good chance that you could make the meter unsafe. Again, this is just for educational purposes. I have some skills working with high voltages, and I'm quite comfortable at the energy levels that I play with here in the lab. Hello again and welcome. We're going to be looking at this Kusuntest ZT102 one more time. During the last video, I benchmarked this AN8002 against the ZT102, and we damaged the 8008. Of course, this doesn't power up anymore, but the ZT102 is fully functional. Of course, we didn't do any transient testing to this. We have another ZT102. This is the first one I purchased. Again, this was badly damaged. So I thought what I'd do in this video is take a look at some of the problems that this meter has and see if we can address some of those. So there's a few things that I don't like about it. One of them is that it uses these split connectors. Another thing I don't like is these fuses that they have. Another thing I don't like about the meter is the fact that they share the current input with the standard volts input. So again, the problem with that, if you kind of trace this through, the input here goes through this fuse and it runs up to this leg of the switch right here. And then this switch goes off to this TVS or diode or whatever it is back to ground. So what ends up happening is you put a transient into this. Of course, the fuse is shorted, and essentially it jumps right across these two contacts back to ground. So this is why you see these get damaged, and when Dave was running the test using his insulation checker, these are the two contacts that were breaking down. The problem next is that once this opens up, that transient continues down this trace here. Of course, it's been vaporized on this unit up to this via where it goes through yet another switch, and then that basically tacks in that node between these two resistors. So this resistor is a 1 ohm, and then this resistor is a 99 ohm. So in the milliamp range, we're using this 1 ohm shunt. They have the facility to use this other resistor here at 99 ohms. It doesn't look like it actually comes into play. That just routes up and goes directly into the IC, it seems. So it's possible that maybe this meter was designed to actually have another range at one point. So what I'd like to do is rearrange it so the current input is actually not shared. I'd like to just be able to do all the current from the one side. So if I can separate this out, this is going to free up a lot of room in this area. So the next problem the meter has is it's got this clamp sitting here, and that's in series with this PTC. And again, this goes back to the IC, but because this is on the back side of the switch, it puts a lot of strain up on the contacts here. And again, that's why you see this trace here has been vaporized. You can see some of the damage between these two contacts. So what I'd like to do is basically put the clamp right up here. So I'm thinking if we could add a couple of PTCs in here, if we get rid of the fuse, and then add a couple of MOVs, we could probably protect the meter quite well. The one leg is again protected by these two resistors. These are 5 megs in series, and then these go back to the IC, so those limit the current. That probably is good enough, but I can see where we would have to rearrange some of the traces on here to make it work with the two PTCs. So I think the first thing we're going to do is try to address the split connector. So I had saved some of the pins out of some of the other meters that I've damaged. Some of these are a nice machine contact. You saw where I'd used these in the UT61E as well. So what I'm going to do is take some of the other pins, which were actually a split type, and I cut these off, and I'm going to wrap this around the end of this and solder these together, and then we'll slide that back inside of the plastic tubing here, and that'll become our new contact. So this is looking at our new connectors. So what I've done is I've taken the plastic out of the original meter that I've damaged, and here you can see I've installed the new barrels. And then what I've done on the back side is I've hot glued these into place. So again, that's just this loop, essentially this piece here where I've cut it off, and I've gone in and I've soldered that onto a machine pin. So the height of these is going to end up being the same. So these will be a much nicer pin. So now that we have some pins, the next thing I'm thinking about is the fuse size. If we went with a single fuse up in the corner, it looks like there's plenty of room in this area. And on the case itself, it looks like there's nothing in this area as well. So I believe that I could actually mount one of these fuses in here without any trouble. And again, we're going to have to change some of this if I go ahead and do that, but I think the first thing we're going to do is cut some of these traces out here and give us a little bit of room in this area to work with. When I ran this on my transient generator, you may remember that when I output the rectified AC, this meter can't handle that. So it actually displays a very low voltage most of the time in the AC mode. And it seems to be just a range problem. So this meter actually has a range switch input. You can see it located on the back. And what I'm thinking is it'd be nice to have access to that button. So again, using the parts off of the original meter that I damaged, what I've done is I cut the front case. That's this gray part right here, so that would be this area here. And I've hot glued that into the case. Let's see, I've just taken my Dremel tool, opened this up a little bit. So this is the base button off of the original ZT102, and I've RTV'd that onto another switch, which happens to be the same size. And we can see that that fits right into here, like so. So now, if we put this thing together, and we go over to volts, we can see if I push our little button here on the back, see we're in manual range, and that works for the millivolt ranges as well. We can see here in the AC volt mode. So I've turned on the generator, it's outputting 120 volts or so, and you can see as I attach the leads again, there it is, about 120. Again, if we go back to DC, there's our 240. Back to AC again. You can see it's in the wrong range. And we'll just switch this down, and there's our 120 volts. So at least it gives me a workaround for the meter. So when I purchased this second ZT102, the first thing I noticed, besides the LCD was kind of washed out, was that this switch feels very tight. So if we open this up and take a look in the inside, so these just pop open here. May be difficult to tell here with the camera, but these springs that are down inside of here are a silverish color. These are actually the springs out of the original meter. The new springs that came with the second meter are a copper color. The only thing you see I did is I added a little lubrication along the detents. So this switch now is actually quite smooth compared to what it was. So you can see I've removed the battery pack, but the other thing I've done is I've removed the PTC, and I've replaced that with just this small jumper. So what I may end up doing is stealing the second PTC and using this for the second leg. Alright, you can see I've got the fuse holders removed. I've also gone ahead and removed the diode. I think what I'd like to do is cut some of these traces. So this first one that's going to go is this guy right here. Again, even if I left this saw intact, I know that if this thing arcs, it could potentially jump across the two contacts here. So I'm just going to go ahead and pull that right out of there. Maybe take it right from here. So again, these 5 meg resistors route down. There's a via here and a via here. So one of them is routing to the back side of the switch, which again goes all the way back to the input. And the other side of this again would go through the switch here, and then you can follow that up and it goes to the PTC up here. So some of these are actually going to have to be routed directly back to the input. So again, if you're measuring in resistance, for example, we need that current source to be able to drive back to the source over here. Otherwise we're going to lose accuracy. I suspect what I have to do is probably cut this trace here, and then this would be our high impedance that's going to go back to the meter. The one I'm not sure about is this one here. I think it might route to this switch and back over to this leg here. So it seems like it basically shorts these two out. The more I look at it, I think that this is the spot that we want to cut it. Probably right here. So even if we screw this meter up, we really don't have a lot invested in it. So we're just going to go ahead and cut this trace right here. Alright, so these are the modifications I've made so far. You can see I've stolen this PTC off the original meter, and I've moved this one here down to this side of the board, and then I've added 2 MOVs. These go back to the ground path. You can also see I've cut some slits in here. This trace here was the original drive. So this would normally get switched in when you're using the resistance or diode check. So that would go through this switch here, which now goes back to this set of PTCs here. So we can see I've cut the trace here, and it routes back to this junction here, which is this PTC, and then going back to ground through this MOV. So this other PTC junction here, which is located here, is now going to route up to our 2 5 megs in series. You can see that right here I've cut another trace. So I've tried to isolate this node right here, and I've routed that also over to the 5 meg inputs. So these I'm going to leave normally attached. These normally would have been switched in, and I'm just going to leave those switched in all the time. Unfortunately, I don't have another switch, so I can't quite make it work the way that it would have originally. So then what we're going to do is place this piece of plastic that I've cut, and that's going to give me a little bit of spacing between this area here and the circuit board. So again, we're still passing, about 1,000 volts through this area here, so that'll just give us a little bit of extra insulation. So it's a little tight. I may end up putting some Teflon spacers in here, but I think the first thing we need to do is kind of clean this thing up. We'll assemble it and just see if it even works, because these are some crazy mods that we're doing, because I'm just kind of guessing at the how this thing would actually work, so it may not work at all. So let's just give it a crack here. So I'm just going through and cleaning up the circuit board before we do much else. One of the things I was going to mention is, you may notice that the original PTC, again, it was up here, and it routed down to this trace, which I've just cut, and I routed that back to the switch, which essentially then goes back to this PTC here in the MOV. So I'm thinking a few of you may have thought, well, we could have left the PTC up here. The problem that I've got is I want to make sure that I have the return path as close as possible to the common input. So I want this MOV sitting as close as I can right down to this ground pad. So that means putting the PTC up here. Otherwise I've got to have the MOV sitting off of this node and find a ground coming all the way back here, which leads to a lot of inductance. And again, I don't even know if the meter would survive when I do that. So again, I just want to have everything tight up in this area here. The only thing I'm going to do is apply a little bit of Corona dope to some of these places where I've cut the circuit board intact in these traces. That should help increase the dielectric strength for this. Probably add a little bit down in this area as well. You can see I've gone ahead and doped up this area. I've also added a little bit of heat shrink tubing over the two PTCs, and you can see I've installed this piece of plastic. So another thing I've done is I've cut the trace for the current sense. So originally there was a trace that went right from this resistor over to this pad, and what we're going to do now is use both of these shunts. You can see I've added a new wire that I'm going to tack in over here, and basically what that's going to do is when we're in the milliamp mode, it will short out this shunt and we will strictly use the 1 ohm. I'm going to leave the original 0.01 ohm in there. There's a 100k ohm resistor in series with this going back to the IC chip, so I'm not too concerned about any kind of transients really coming in through this yet, but I would like to add a bigger fuse. So these are some of the fuses that David supplied. You can see if I were to add that, that would be quite long. This is one of the Asia fuses. Again, this is 1 amp. I think this came out of the UT61E that I had modified. So what I'm thinking to do is add these new fuse holders and use these couple of pads here, cut the traces up in this area, and mount this thing right here. There's plenty of room inside the case to use that area, so I think that'll be a good setup. You can see I've gone ahead and mounted our new connectors, and I also have our new fuse holder in place. This is a small L channel that I've cut here. That's to separate these two sense resistors from this side. And if we look at the original clamp, this is a 6V8C. This is a bi-directional part that's made by TI. The maximum breakdown voltage of this part is 7.14 volts. So what I've done is I've gone ahead and attached that right from the fuse over to the ground side. So I believe that's the end of it, other than cleaning up the display here a little bit. And I'll go ahead and mount the battery pack, and then we can give this thing a try. Again, this will be the fuse that I plan on using. Alright, we'll see here if everything lines up. Hopefully it just fits right together. It's not the neatest looking workmanship, but let's see if the lid will close on it. And she's a little tight with the battery pack riding high. Let's see, it's a bit snug now. I think it'll be all right. All right, so I've got the 2 meters in series. You can see I'm applying roughly 1.84 milliamps right now. The 2 meters are close. Looks like there's a bit of a gain problem maybe with the 102. Yeah, it looks like the gain is off a little bit on this now. So you can see 130 milliamps versus 125 roughly. Still not too bad for what I've done with the meter. I probably could trim this out a little bit. So I've changed this just slightly. You can see I've also changed some of the resistors up in the current shunt area. So I added a few resistors here to trim in the milliamp range. And then I've changed this to a 10x gain. So essentially you're going to gain 1 digit off of the milliamp range when you select the amp side. So it's going to be difficult with the Corona dope here to tell what's going on. So I basically marked it on this board. Essentially, I cut this trace at this location here, and I cut it here, and I cut this trace here, and then I run a jumper from this side over to this side. And then I put a jumper from this side over to this center leg. So I just added the Corona dope. We have to let this thing dry a little bit, and then we'll put it back together and give it a shot. Alright, let's just do some basic functional tests. See, I just left the back off of the meter. Again, I have no idea if this is going to work. I would not be surprised if we don't have some problems. So we'll start with the 5 volts. That looks fine. This should be 0 and this should be 2.5. That looks good. Let's go to AC volt. It should be 2.5. And this should be 2.5. That looks fine. Let's go to frequency. It should be 60 and this should be 60. It should be 30 and 15, 120. Let's try duty cycle. It should be 50%. This should be 115 millivolts or so. Yep, normally 118 is what it shows. Let's try our resistance mode. This will be a short. Looks fine. This is with 0.5 ohms, 1 ohm, 50 ohms, 100 ohms, 1K, 10K, 100K, 1 meg, 10 meg. And again, this meter can read up quite high, so this will be 40 meg. Looks good. So it looks like the resistance still works. This is continuity test. Looks fine. Diode check. This is with a short. And here's a single diode. 2 diodes. And 3 diodes in series, so that looks fine. In capacitance mode, you can see here's a bit of a problem. So this used to zero out. Of course, we've added these 2 MOVs, which have a fair amount of capacitance, it looks like, so it now reads about 100 picofarads high. So I'm expecting this is going to read 250. This will be 1 nanofarad. And 0.1 microfarads. It's too bad this doesn't have a way to zero this out. This is with 1 microfarad. This is with 10 microfarads. And this is 100 microfarads. So all these ranges seem like they're fine. It should be roughly 500 degrees. Again, I should be able to vary this down to room temp roughly. A little over 1,000 degrees. And this would be our DC millivolt range. That seems to work. Alright, so now let's try the current mode. Again, 100 microamps. Fairly close. Alright, you can see I have my high voltage power supply out. What I'm going to do is just attach this to our meter and we'll put it in the volt mode. Here's 300 volts. There's 500, 600, 700, 800, and right there we're limiting. So about 815 volts. So let's take out our fuse and we'll attach it across our fuse input. And let's just see if it breaks down at all. So that's 1 kV. There's 2,000 volts. So it looks pretty good. Alright, I think the next thing I want to do is go ahead and repeat our ESD test. Again, this transient generator basically follows the IEC standard. So this is going to again apply a 4,000 volt peak at 15 amps and under 1 nanosecond. Again, I'll be applying 5 transients to each mode of the meter, and we'll be applying both positive and negative pulses. Alright, that's it. So again, this will be 5 volts, and this should be 2.5, and this should be 2.5, and this should be 2.5. This should be 60 hertz, and 60 hertz here as well. 50% duty cycle, that's correct. Again, this will be about 118 millivolts. Again, this should be about 20 millivolts. This is with a short, 0.5 ohms, 1 ohm, 50 ohms, 100 ohms, 1K, 10K, 100K, 1 meg, 10 meg, 40 meg. Continuity test. So here's 1 diode, 2 and 3 diodes in series. This is with 1 nanofarad, 0.1 microfarad, 1 microfarad, 10 microfarads, 100 microfarads. And again, this should be about 500 degrees Celsius. So it appears that the meter survives that test just fine. So I have our modified ZT102 attached to our transient generator. I'm just going to enable the AC line voltage. You can see it's measuring 238 volts. If I switch it to AC, again it's reading 1.2. That's not correct. I'll just select our range switch here. And you can see it's roughly 120 volts. What I'm going to do now is set the meter to all of its different functions with the AC applied, and let's see if this causes any problems. Alright, let me go ahead and functional test it. So the meter passes functional test just fine. Next, what I'd like to do is start transient testing it. Alright, when I tested this original meter, it was damaged at 3000 volts. So what I've done is I programmed our generator for 3000 volts, and we're just going to use that as our starting point. So again, this will be a 3000 volt, 100 microsecond full width half height with a 2 ohm source, and again we'll be applying positive and negative transients to each mode of the meter. Alright, that's it. Alright, the little Kusuntest survived that test just fine. I've reset our generator to put out its maximum voltage, so this is just shy of 6000 volts. We'll go ahead and repeat this test. The reason I'm not stepping through this isn't any data I'm going to collect. Again, I'm not recommending that anyone would go through and actually modify a meter like this. First of all, it's not worth it just from a price standpoint. You figure by the time you buy the MOVs, cut up the circuit board, all your labor, it just doesn't make any sense from that standpoint. The other problem is from a safety issue. Again, you go through and modify a meter like this, it could become very unsafe to use. So don't ever do anything like this. So again, this is going to be 6000 volts with a 100 microsecond full width half height, 2 ohm source impedance. Again, we'll be running positive and negative transients. Well, I think that's the end of her. So it looks like we made some improvement. Unfortunately, not good enough. Okay, I can tell you what happened right now. I don't even have to lift this board out of here. Basically, you can see the clamps down here were destroyed. And that's because this little pissant PTC broke across. Again, I've said that in the past. Companies will put these little shitty ass PTCs in there. And again, I didn't replace them. These are what this meter was supplied with. And this one here broke down, flashed across it, and all that energy then went right into our clamp. And of course that goes right into the IC, and that was the end of her. So unfortunately, I'm afraid there's nothing else we can really do with this. I can show you what the PTC looks like. Oh, there you go. You can see it's just blown all to hell. Let's have a look at the other one. So the other one looks okay. No visual signs of any cracking. It's just the one here. Well, that's another reason that you don't want to go modifying a meter like this. Again, I spent quite a bit of time going through figuring out how to mod it, then make the mods, and then in the end the meter still gets destroyed. Well, I think that's going to be it for this video. Hope you enjoyed it. Till the next meter. Later.